So I'm going to start. Today I'm talking about the RISC-V vector. So specifically, I will go through, explain how to use the RISC-V vector in the AI operators. So I did some benchmark measurement for two open source libraries. So self-introduction about myself. My name is Guodong. I'm coming from RISCstar Solutions. RISCstar is a company that provides software optimization services for our customers. So today, the two open source library I'm going to talk about today is OpenBLAS for linear algebra operators, and the sleeve that's for nonlinear math libraries. So first, I will go through the RVV design logic, some ideas about using RVV in writing the AI operators. Then I will bring up the main part, is the comparison of using RVV and the scalar in the OpenBLAS and the sleeve library. So finally, I will touch a little bit about perf. So the platform I did for the measurement is the hardware platform is the SpacemiT K1, which is the commercially available RVV 256 vector length RISC-V processor. So for about $100, you got a developer board, easy. So software platform, I'm using the Fedora Remix. Thanks to the Fedora vForce team, they provide support for performing some of the benchmark testing here. And toolchain, I recommend everybody to search and download the RISCstar toolchain. That's an open source version. You have the source code and the pre-built binary, so you can check it out. It has the vector optimization, of course. So let's start. RISC-V vector has a lot of unique features. So like their core programming model, it switched from predicate to vector length. I will talk about that later. Its register file design is not overlapping with the float registers. It has separated, dedicated float register file and the vector register file. So in this page, I will talk about the two features on the top. So these are usually the hurdles, the first hurdles people moving from other architecture to RISC-V vector will meet. So first, it's about vector length multiplier, MUL. So with that, you get to access, in one instruction, you get access 2 or 4 or 8 vector registers. So they are all named at the first register. So if MUL equals 2, so with one instruction, you can access 2 registers, 2 vector registers. The downside is you got the total amount of registers you can access got halved, right? Previously you have 32, now you have only 16. But the good thing is with one instruction, you got access more data, get to process more data elements. So with that, I bring up another concept, which is also important. It's about the application vector length. So there are these concepts like AVL, application vector length, and VL max. And then you have the final one is the VL. So AVL, application vector length, is like some software requirement. It's the user's requirement. It's something you tell the hardware what you want to do. So for example, here we have MUL equals 2, so I can process 16. The hardware will say VL max will be 16 elements. So the hardware will say I can process 16 elements at one time. The software said, okay, AVL is 100. I have 100 elements. So now the negotiation result is vector VL, the actual VL. VL will be 16. Okay. Think about the final loop. The final loop, maybe the application said I have 7 elements to process. So the hardware say, okay, I can handle 16 elements. Then the negotiation result, VL, will be 7. So that's how you program using RISC-V vector. Okay, so when you're porting the AI operators, usually the first step you met is how to handle the loops. So with ARM SVE, it is guarded by the predicate. But for RISC-V, we use another concept. We use the vector length. It's called vector length driven. So just I explained in the last page. So vector length is the negotiation result between the software and the hardware. So software, just as a programmer, you just need to tell what you want. So in the loop, you can, originally everything you can use to the maximum 16, 16, 16. Then in the final loop, the negotiation result will be just the tail elements you need to process. It may be 4 or whatever. The key concept here is the loop body is just the same. It keeps the same. You do not have another code section to handle the tail iteration. Yeah. So then the second step will be a little easier, but you still need to be careful comparison between moving the original vector intrinsics to the RVV equivalent. Yeah, there are a lot of instructions here, so people should be very careful. Here I don't want to go through the details, but I really recommend you take this new course, which will be coming online soon. It's co-developed by RISCstar and the Linux Foundation. It will be online, free to access. So, yeah. Okay, so let's talk about AI operators. In the top level, so the AI operators can be categorized into 2 groups. One is the linear operator, the other is the nonlinear. For linear operators, over these past 2 days, a lot of people talk about that, like GMM, matrix-matrix multiplication, and GMV, matrix-vector multiplication. But not many people talk about the nonlinear part. Yeah, so today, I'm going to show you some data on that. That counts about 10% of the computing in AI inference. It's like normalization or activation functions. These are using nonlinear. So first, go through the OpenBLAS. It's very popular. It's appeared in several speakers' slides. So generally speaking, OpenBLAS supports RVV. They use 2 methods. One method is for BLAS level 1, level 2 APIs. They use the entire vector length. It's vector length agnostic. So for level 3 matrix-matrix multiplication operators, they use the fixed length. There are 2 flavors, like one for GVL 128-bit, 128-bit length. The other flavor for GVL 256. So there is a reason they choose different strategy. The level 1, level 2 are memory bound, so they can, as much data as possible, you can read. That's good. But for level 3, it is computing bounded. So it really doesn't matter how much data you can read. So it's bounded by the processing power. So that's the reason. And here is the comparison between the ARM SVE and RVV. So when I prepared this slide, I tried to use that, to compare, this instruction from SVE mapping to this instruction to RVV. But a detailed look. This is the microkernel for SGMM. A detailed look, you will find there's a difference. So for SVE, for example, if you have 128 base vector length, SVE can handle 4 times 8 elements in each of these loops. But on RVV side, it is handling 8 times 8, about doubled. So what's the difference? Why is the difference? So look at the detail. You found for SVE, they are using actually 2 loops. So when it processing this 4 times 8 iteration, at the same time, it is reading prefetch for the other 4 rows for the next iteration. So there are instructions very clear. It's PRFM, that's the prefetch. Also the LD1 RW, that is also another type of prefetch. So that's how SVE handle that. For RISC-V side, at this moment, it is not using prefetch at all. So RISC-V has the cache block prefetch extension. It is part of RVA22, also mandatory in RVA23. But for some reason, it is not being used in the OpenBLAS implementation yet. So I think this is should be a next step for we in the community to explore that using prefetch to further optimize the RVV solution, RVV microkernel. So here are some performance comparison result. I compared the double precision and single precision GEMM with the several flavors, vector length 128, vector length 256. Also compared some different MUL configurations, length multiplier 1, 2, and 4. So there are 2 observations. First, how the vector length impacted the result. The second one is the length multiplier. So here for vector length, in this page, vector length, you see everything looks like it's working in our expectation. With vector length getting wider, the performance, the data elements being processed in 1 second get increased. Not doubled, but it's increased. So vector length clearly is a good thing here. A detailed look, if you compare the efficiency, which I mean, so ideally, theoretically, from scalar to vector, the vector length is doubled. For DGEM, the vector length is doubled or quadrupled 4 times. So the M flops should be doubled or 4 times as well. But in fact, it is not. So that's somewhere the software tuning should kick in. So you cannot rely on compiler itself. You have to explore the other reasons why the processing unit is not fully in doing their job. So the numbers show like DGEM only achieves 48% of the theoretical efficiency. For SGEM, it's achieved 38% of efficiency. So both have a huge opportunity for further optimization. So here, next goal is to compare the length multiplier, whether we should use that. So the concurrent is very complicated. There are sometimes length multiplier is helping us, like the red arrow shows. You use the bigger length multiplier, you get quicker. The size is the matrix size. So here, matrix size from 256 to up to 4K. So sometimes, like the yellow arrow shows. So length multiplier is just getting things worse. It is not helping us. It's instead the total processing time increased. So that makes me think like a simple conclusion. So like a recommendation I put here, maybe I just say maybe we should consider the matrix size tuned adaptive MUL settings. For example, for SGM size 512, maybe we should use MUL equals 2. But for other matrix size, longer or bigger than 4K, we should just stay in MUL equals 1. But the reason I say maybe is, because these are whatever matrix size it is, the microkernel in GMM implementation has the same dimension, like 4 times 8 or 8 times 8, right? So the reason some matrix size works better, some matrix size works not that well with MUL, maybe the root cause is not in the microkernel itself, it's in the level 2 or level 3 cache capability. With different size of the matrix, some of them cannot fit in the level 3, level 2, level 3 cache. So that makes the low efficiency in the follow-up microkernel processing. So again, that points to fine-tuning in the macro architecture level. So moving on next, I also in this project measured the performance of the nonlinear operators. Nonlinear operators can be, it's also many different types, like a classifier or activation function or the normalizer. All these are mandatory, but it's not the major computing operator, but we need to, they are still there. They are about 10% of the total computing. So chasing down these nonlinear functions, you find it's implemented by some mathematic functions like exponential, hyperbolic, tangent, or square root. So good news is there are already many SMD implementations, speed-ups for these nonlinear operators. So SLEEF is an open source implementation. One of the open source implementation is a good one, in my opinion. And it can support many different architectures from x86 to ARM to RVV now. So yeah, here, maybe I should explain a little bit about the SLEEF implementation. In SLEEF, it defined a common C file for each of the functions, like XLP function. And under the C common function, there are header files defined for each of the architecture. Like for SVE, you have helper arm SVE.h. For RVV, we have helper RVV M1.h, RVV.m2.h. So for anybody want to get a comparison between how ARM SVE and RISC-V RVV implementation is, the intrinsics mappings between two architectures, you can just, SLEEF is a good project for you to look at. So in my measurement, I compared the basic math functions, EXP, hyperbolic tangent, and square root. So these are these are important routines for AI. Because these operations are memory bounded, so it's natural. We do not limit their vector length. We just use whatever we got. We use the maximum available vector. So in SLEAF, there are two implementations. One is RVV with LMUL1. Another implementation is RVV-M2, length multiplier 2. So here, the performance from this chart, it looks like much better, much cleaner than GEMM. So with bigger LMUL, you get a higher performance, which is good. So here is in this page, I compare everything with the scalar implementation. Scalar is 1.0. That's the base. So for RVV-M1, you usually get 2 times performance, and then RVV-M2, you got 3 or 4 times. So here is a comparison between RVV-M1 and RVV-M2. So the conclusion is like longer LMUL, bigger is better, right? The only outlier is tangent H. Everything else shows good result with RVV-M2. So it basically increased the performance for 1.4 times. That makes me think maybe we should try some even bigger MUL, like length multiplier equals 4 or 8 or something. So SLEAF itself supports not only math libraries, it also supports some DFS function that limits its usage of bigger MUL. But if we only need exponential or square root, we can easily, for sure, we can try RVV M4 or M8. Using SLEAF, I write a GELU kernel, a real one. So for GELU kernel, there are 2 implementations methods, actually. One is the exact form. The other is using the ERF function, error function. Another implementation is using is approximation using tangent H. So with both implementation, we see RVV-M2 has about 2 times speed up comparing with the scalar baseline. So really, see here, RVV is helping us, and length multiplier is worth to try. I do notice that yesterday in another session, the engineer from TensorTorrent discussing the auto-order auto-order pipeline microarchitecture. The conclusion from them is maybe in auto-order pipeline, they do not recommend length multiplier equals 2 or 4. So in my test, I'm using the in-order pipeline, SpacemiT K1. So I really want to someday have a hands-on in the TensorTorrent Escalon CPU maybe to test it out, how RVV-M2 behaves on their platform. Yeah. Okay, that's come to the final part of my talk.
I'm sorry, we're like
yep.
7 minutes over, so I got to cut you off.
Okay. Okay, yeah, that's about it. So for perf, maybe just need, what we really need is upstream. So far, everything is just in their vendor kernel. Yeah. Okay. Thanks for people hanging there.